Hey chemistry students, we're going to do lesson 11.2 talking about measuring concentration.
And our first goal or objective is to define concentration and explain various ways concentrations are measured.
And there are a number of different concentration measures. The second one is use molarity. That's going to be the most important concentration measure to perform different calculations involving amounts of solute, volume of solvent, and concentration.
And lastly, we're going to calculate the concentration using mass percent, mole fraction, molality, and parts per million and parts per billion. These are all seen on a sheet in your packet. I believe it's the second sheet in your packet.
Yeah, it's right inside the cover, and we're going to touch on each one of those in this lesson, so let's get started. Okay, so first of all, we're going to discuss concentration. And we can kind of roughly or qualitatively define concentration as the strength of a solution. So if we look at the solutions over here in the picture, they're both made by dissolving blue food coloring in water. So there's blue dye molecules mixed with the water. So which solution is most concentrated, Mr. Hunter?
Well, looking at it, you can see that one is a more clear blue color. You can almost see through it, while the other is a much more dark blue.
Much more intense blue color.
And that means you told me you use the same amount in each. You use 3 drops in the left one and 3 drops in the right one. So just by sheer common sense, the one on the right has more water in it, so therefore I would consider that to be less concentrated. So the one on the left, the darker blue one, would be the more concentrated.
So this one's clearly the most concentrated. This one would be, like you said, less concentrated, or sometimes we would use the word it's the most dilute.
And I kind of jumped you on that when I didn't see the last question there.
So the third one's a trick question. They both have the exact same amount of solute, exactly 3 drops of blue food coloring, or at least relatively close to the same amount. But we're spreading that solute out through far more solvent in the larger container, so it's less concentrated or more dilute. So we can qualitatively define a concentrated solution as one which has a large amount of solute in an amount of solvent, and a dilute one would be the opposite, a small amount of solute in an amount of solvent. Of course, describing things qualitatively is not always the best way to go when we're trying to be exact, is it?
No, in chemistry we like to be as close to exact as we can, and it helps us to talk amongst each other.
That means we're going to involve some measurements and calculations so we can quantify the concentration, so that's where we're headed next. Let's start there.
Alright, so the first type of concentration we're going to talk about is the mass.
Let's define overall the word concentration first, qualitative or quantitatively now.
Sure, so concentration is the measure of the amount of solute per an amount of solvent. So the first type we're going to do is the mass percent, also known as percent by mass. And you can see that it is mass percent equals the mass of the solute. Remember, the solute is the thing that has less in the solution, divided by the total mass of the solution. That would be the mass of the solute plus the mass of the solvent. You multiply that by 100 and you'll get your mass percent. So for our first example, they're telling us that find the mass percent of 125 grams of a solution containing 6.0 grams of dissolved sodium chloride. So the 125 figure is the total mass of the solution. The 6 grams is the mass of the solute, so that goes on top, and below would be the 125, and we're going to multiply by 100. Notice your grams cancel to give you 4.8% using proper significant figures. So that's mass percent. They can be a little more tricky, but not much. So there's our.
The only thing that may be a little wrinkle would be, instead of giving you the total mass of the solution, they would tell you, well, it's this much solvent.
Yeah.
And then you'd have to add them together to get this bottom number. In this case, you didn't need to do that.
Nope. All right.
So a second measure we can use for concentration is parts per million, or we could even use it in parts per billion. This is really used a lot in environmental chemistry, where we're talking about, say, the amount of oxygen dissolved in water, or the amount of some pollutant that's present in the water solution. So parts per million, the equation would be like this. You take the mass of the solute, and you divide by the mass of the solution, which so far is exactly like the percent by mass, right? The difference is then we're going to multiply by a million, 10 to the 6th power at the end, and that's going to give us our parts per million. Now, I didn't add this on here, but you could do the same thing and get ppb, which would be parts per billion. So we're going to take the mass solute divided by the mass of the solution, and then we would multiply by a billion.
Yeah, 10 to the 9th.
10 to the 9th. So the only thing you need to make sure of is that the masses need to be in the same unit so they cancel out. Alright, so we have an example problem. Let's work through that. What's the concentration of lead if there's 1.9 grams of lead dissolved in 300 kilograms of water? And like I just said, the masses need to be in the same unit. So we have 1.9 grams
divided by 300,000 grams plus
300,000, 1.9.
Yeah, but using sig figs addition rules, that wouldn't even add on.
That's right, because this one's the least significant place was the thousands place.
Yes.
So we're just going to make it 300,000 grams.
And honestly, it wouldn't make a difference.
No, it wouldn't make it. When you rounded it, it wouldn't make a difference. Anyway, oops, I forgot times 10 to the 6, which is going to give us the parts per million.
Yep, and it equals out to be 6.3 parts per billion.
ppm. In parts per billion, it would be
0.0063.
0.0063, because we'd multiply by 10 to the 9th, ppb. And if you look at like what the government sets as, like, say, maximum acceptable limit of certain pollutants, like how much, of this is allowed to be in drinking water, or that, a lot of the times it's expressed in these units of parts per million or parts per billion, because if it's a toxin, some of them are toxic at very, very slight levels. Okay, so let's that's an example of that. Let's move on to another concentration measure.
All right, molality is a more common type of concentration unit than the previous two. Molality are the moles of solute per kilogram of solution. This is a very important one for scientists who are doing concentration measurements in let's say regulated temperature areas, because it doesn't involve a volume. It's therefore independent or unaffected by what temperature it is. Since that is the case, molality is your more exact concentration measure from the day-to-day if you are not in a controlled area.
So if you took a solution from a cold place to a warm place, its molarity is going to change slightly, or its concentration if we're basing it on volume, but its molality would not change.
Yeah. So you see below, it's little m, it stands for molality, is moles of solute divided by kilograms of solvent. So down in our example, they give us 0.32 grams of oxygen, which turns out to be 0.01 moles of 0.010, I guess, moles. Oh, you're doing the math there for him.
Okay.
Yeah.
Well, I might as well now. At this point, I'm kind of committed. So that would be 32 grams, 1 mole. So we're actually finding the number of moles here, not out.
Yeah.
So that comes out to, what'd you say?
0.01.
0.01 moles of O2. And now we can do our
divide that, yeah. Now you divide that by 0.75.
0.01 moles and 0.75 kilograms of water.
It turns out to be 0.013. We didn't use proper sig figs at the top there. It should be 0.010 moles. So the final answer should be in 0.013 molal, or m,
little m, or we could write it as moles per kilogram.
Yeah.
Either one's acceptable.
All right.
It's supposed to be an or.
Okay. All right, let's go look at the very last type, molarity. Oop. All right, well, I was wrong.
He was wrong.
It's mole fraction next.
Look at mole fraction, which is another way to express concentration. This one's not all that common, but it's useful when it's not really clear what is the solvent and what's the solute, like mixtures of gases, mixtures of liquids. So what it is the moles of the substance in question per the total moles of the substances in the mixture. So for example, would be mole 1 would be the moles of the whatever substance you're interested in. The denominator is the sum total of the molar quantities of all substances in the mixture. Okay, so we have an example problem. The gaseous sample contains 0.23 moles of O2, 0.77 moles of N2, 0.31 moles of H2, and 0.031 moles of H2, and 0.045 moles of methane.
And they want
What's
to know
the mole fraction of O2?
Yes.
So how do we do this, Mr.
So
Hunter?
the top one is going to be 0.23 moles.
0.23 moles of O2. We're going to divide it by the sum total
of the bottom,
all of them.
which I believe it adds up to 1.076. I believe. Let me check that again.
So we have 1.076 moles of gas total in the mixture.
Yes, I did it right. And that equals out to be 0.21.
Now what unit would go on that?
Oh boy, all your moles cancel out, so nothing.
So it's just the mole fraction is 0.2102. So there's 0.21 moles of O2 per mole of moles per mole, I guess, which would be. But that's the mole fraction. So it's roughly 1/5 of that mixture is or molecules of oxygen.
All right, now let's go into
Now
molarity.
let's go to the molarity.
All right, so here's molarity, which is the most common concentration measure in general chemistry.
So underline that, put some little stars and explosions around it, because this is the one that you really, really need to know.
And you've seen it a lot already this year and may not have realized it. Anytime you've done something with a concentration of a solution or a solution, there's a big M next to it. And you guys didn't understand what it meant or how to read it. When you see the big M, it just means molar. So what molarity is the moles of solute per liter of solution. And the equation is very simple. It's just big M equals N, which is moles of solute, divided by volume, which is your liters of solution. It can also be written with a bracket around it, down there in the bottom. That bracket means it just says it's the molarity of HCl, which is the molarity of hydrochloric acid. So if you see a bracket around some kind of chemical, it's a shorthand notation for molarity.
And sometimes we would just say it's concentration of HCl, which is the same thing because molarity is a concentration measure. So let's get to an example problem.
So down there we got 0.31 grams of HCl, so we got to turn that into moles. So that turns into 0.0085 moles.
And I'm not going to show the math for that one.
At this
so
point,
we have
you
that
should
many
know
moles
that.
of HCl
Divided by 1.27 liters gives us a final concentration of 0.0067 molar.
big M, or we can write moles per liter, because big M and moles per liter are the same thing.
And this, like I said, is the most common, so get used to doing this type of math. So here are your two post-video questions.
No, these aren't post-video
Oh, these
questions.
are, why
We're
are you
still
doing this to
going.
me?
We're still going.
All right,
This is an epic video here.
Apparently
So we're going to look at what you can do with molarity. And one of the really common uses, and I know Mr. Hunter and I did this constantly in the back room setting up for your labs, is dilution problems. Because we buy the acid in concentrated form. It's cheaper to ship it that way, and then we can dilute it down to whatever. So the basic equation is this: the molarity of the solution at its first concentration multiplied by its volume equals the molarity times its volume the second time. And if you look at the math, multiplying the concentration by the volume you have is the number of moles. So the number of moles is staying constant, but we're adding more solvent and diluting it down. So if you know any three of these, the fourth can be calculated. So for example, if I wanted to make 3 liters of a 0.5 molar acid, the stuff in the bottle, the concentrated stuff we have, is 12 molar. So I would need to know how many milliliters of the concentrated stuff do I need to make 3 liters of 0.5 molar acids. So this is my V2, this is my big M2, this is my big M1. So my unknown is V1.
Yeah.
All right. So I just solved that equation for V1. That's going to be M2 times V2 divided by M1. and this will tell me how many milliliters I'm going to need. And you don't need to convert this to liters. It's just if you're starting with milliliters, your answer comes out in milliliters. So I know that I want to end up with 0.5 molar HCl. I'm going to multiply that by 3.0 liters, which is what I want to end up with. And my original starting molarity was 12 molar.
And you do the math on that and convert to milliliters in the end, you'll find out it's 125 milliliters.
125 milliliters. With the sig figs got a little wonky because
it's going to be 100 milliliters then.
So it would technically round back to 100, but maybe if this was 0.500, then we'd be okay with.
130 would be better. All right, so there's a very useful tool in chemistry that you'll definitely apply.
Yeah, you'll try that, and we'll do lots more practice with all these. And again, we want you to be at least familiar with the rest of them, but we want you to be fairly proficient with molarity.
Yeah.
All right, now it's time for your post-video questions.
Yes, it is.
All right, so there they are. So the first one's kind of a non-calculation. Explain in words the difference between molality and molarity. And then for the second one, we're going to have you do a mass percent problem. There's the information. Notice that I told you the amount, the grams of water and the grams of sucrose. I did not tell you the total mass of solution. You're going to have to figure that out.
Yes.
Have at it. We'll talk about it in class the next time.
Have a good day.